We still don't really know how AI thinks, and that's not a small problem. The more we use these systems for medicine, law, education, and science, the more it matters that we can look inside and understand what's actually going on. Right now, with most large language models, we can't. You put a question in, an answer comes out, and everything that happened in between is essentially invisible. Researchers call it the black box problem. And a team at EPFL, the Swiss Federal Institute of Technology in Lausanne, thinks they've found a genuinely new way to crack it open. Here's the basic issue with today's AI. When a standard language model sees a question, it doesn't reason through it the way you or I would. It's more like pattern matching at a massive scale. It's seen billions of pieces of text, and it's essentially asking, what kind of answer usually follows this kind of question? It's fast, it's often impressive, but the internal logic is murky. You can't easily trace why it said what it said or which parts of the input it actually weighted as important. The EPFL team took a different approach. Instead of starting from the architecture that most modern AI is built on, they designed a model that's structured more like the human brain, not in a metaphorical sense, in a functional sense. The model separates out different cognitive roles, the way different brain regions handle different tasks. There are parts of the model that handle attention, parts that handle memory, parts that control what gets passed forward and what gets filtered out. What that gives you is something you don't usually get with standard models: visibility. Because the components are distinct and their roles are defined, researchers can actually watch what each part is doing during a response. They can see which pieces of the input the model is paying attention to, how confident it is at different steps, and where it's drawing on stored knowledge versus actively working something out. Think about the difference between watching someone solve a math problem in their head versus watching them write it out on a whiteboard. The answer might be the same, but one lets you follow the logic. That's what this architecture is trying to do for AI. This matters for a few different reasons. The first is trust. If a doctor is using an AI tool to help interpret test results, they need to know the model isn't just guessing confidently. They need to see the reasoning. Same goes for a judge, a financial analyst, a scientist running experiments. Right now, with most models, you just have to take the output on faith. That's a real limitation. The second reason is debugging. When a model gives a wrong answer, figuring out why is incredibly hard with a black box system. You can tweak inputs and see if the output changes, but you're still guessing. With a more transparent architecture, researchers can actually pinpoint where something went wrong in the reasoning chain. That means faster improvements and fewer mysterious failures. The third reason is safety. A lot of the concern around powerful AI systems comes from not being able to predict how they'll behave in new situations. If you can actually inspect the model's internal states, you have a much better shot at catching problems before they cause real harm. Now, to be fair, this approach does come with trade-offs. Brain-like architectures are more complex to build and can be harder to scale. The raw performance of this kind of model isn't necessarily going to beat the biggest standard models right out of the gate. Training it requires more careful design decisions at every level. But the EPFL team isn't really trying to win a benchmark competition. They're trying to solve the interpretability problem, and that's a goal the whole field agrees is critical, even if there's no consensus yet on how to get there. There are other groups working on interpretability from different angles. Some try to probe existing models after the fact, basically reverse engineering what they're doing. Others add monitoring layers on top of a model without changing the model itself. The EPFL approach is different because interpretability is baked into the structure from the start. It's not an add-on, it's the design. What we're really watching here is a split forming in how researchers think about the next generation of AI. One path is bigger and faster, scale up the existing approach and deal with interpretability later. The other path is let's build systems that are transparent by design, even if that means accepting some constraints. Both paths are serious. Both have smart people working on them. The fact that a team has now built a working model using a brain-inspired architecture and used it to actually peer inside the reasoning process is a meaningful proof of concept. It's not the end of the black box problem, but it's a real crack in it, and given how much we're starting to rely on these systems, that crack is worth paying attention to.